So when it comes to the rather introduction to differential equations, right, we have to kind of sort through a lot of verbiage and notation and definitions to really kind of understand what's going on, because otherwise you'll be able to do the initial procedural work. I don't think that's particularly difficult compared to some of the stuff later in like Calc 2, for example, especially like with later series sequences and things like that. Like working through a lot of the initial ODEs is actually rather easy, but knowing what's actually going on is actually the difficult part. It's really very language based, so I think it's best to kind of go over that first and also do a refresher on some things, and then from there we can kind of proceed towards actually solving things and having a better understanding of what's going on. So the first thing to understand with differential equations is the definition of a differential equation, and that is an equation that's containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables. That is said to be a differential equation. And when we talk about differential equations, it's also important to remember that there are different classifications, types, orders, and the different linearities of differential equations to keep in mind. So when it comes to differential equations, we really have to focus on the classifications to really begin starting to understand what we're working with. Obviously, as far as type goes, there's going to be ordinary differential equations and partial differential equations, and we're really going to focus more on ordinary, since partial requires that you have learned how to do partial derivatives, which usually doesn't come into play until either late Calc 2 or early Calc 3, depending on the program or textbook that you're working with. So we're not going to touch on those for now. And really, I mean, a lot of the different techniques we're going to use kind of apply to those anyways. So you're going to kind of learn, by proxy how to work with those just from messing with ordinary differential equations. And so speaking on the order and linearity of differential equations, obviously you'll see a lot of, intimidating notation, a lot of different things like the Leibniz notation or the prime notation, Newton notation or dot notation. And really all that is just different compact ways to express a differential equation. And as far as that is concerned, we can look at something like this. I think would be, a pretty compact way to do the prime notation, right? This is kind of a very easy way to understand it. We have the function, or rather the variable y, and it's being differentiated once here, and then it's being differentiated twice here. And so because the maximum amount of times it's been differentiated is 2, we would say this is a second order differential equation, right? It's really as simple as that. You just look for the highest derivative, and then based on that, that's going to be the order of the differential equation. And then we have the actual linearity of a differential equation, and that is a little bit more kind of not so easy to get at first. You might have to spend some time practicing and working through that, which we will do some practice of doing that and kind of explore how to do that. But really the linearity is just addressing it's a little bit hard to kind of latch onto at first, but so I'll try to do my best to make it as simple as possible. But it's really about the scaling and contribution of the different variables, right? So before we move on to that, I just want to, express like this would be, the Leibniz notation, right? This is a little bit better if you're trying to communicate all aspects of the differential equation, right? Because you'll see the independent and dependent variable at the same time. And the independent and dependent variable, that's just, notating what variables or functions are being evaluated with respect to each other, right? We say that in this case the independent variable here would be x because it is not dependent on changing of the y variable, right? The y variable is going to really get a lot of its scaling and power contribution from the x variable, and that's really as difficult as it gets. It's very similar to with just a regular function, f of x representing, you could say that that is equal to y. Of course, we would say that the x variable in this case would be the independent variable because it doesn't scale off of anything else, right? It's just itself, right? You can write it on a graph. X goes this way, and then y goes this way because y is an output of the input being x, right? So as say we go over 1, then the output is 1. We go over 1 again, the output is 1 higher, and it keeps going. And that's a typical linear function. That's how it can be thought of and represented as. And so when it comes to the classification of differential equations, right, we're going to have different things such as ordinary differential equations and partial differential equations. Now, since this is, the introductory work for the differential equations, we're not going to really discuss partial differential equations too much. I mean, you'll see the notation for it, off the bat here, but really that's, you don't really work with partial differential equations towards until like early Calc 3 or perhaps late Calc 2, depending on your textbook or course. So we won't worry about them right now. You can kind of look at it. I don't think they're particularly more difficult. It's just, you have to have known how to do a partial derivative before you can really start tackling partial differential equations. But it's really the same principles, right? You're just doing changing rates with certain respect to different variables and whatnot. But again, when it comes to differential equations, especially ordinary differential equations, the ones that we're going to focus primarily on for this video and the next few videos, then we have to discuss things such as the order, the linearity, and of course, the type. And again, that is just going to be ordinary. But again, going back to linearity, essentially, again, what you want to focus on is the actual function or independent variable, or rather dependent variable, sorry, that is being kind of worked with, and making sure that its contributions are through addition or subtraction rather than any other particular operation, right? You're really looking at the operations involved with that variable of interest in the differential equation, right? So in this case, this is linear because each of the derivatives of the variable y and y itself are only interacting with things other than itself. And again, kind of explaining this without incredibly precise mathematical terminology is kind of difficult. So again, I'll try to do my best, but I think it's important to kind of think about contribution and scaling when it comes to this to be able to understand linearity. And you'll see what I mean here, right? So if we have, say, I don't know, cosine of x times y prime plus, or y prime prime plus y prime plus y equals 0, then you just simply ask yourself, to find out, is this linear? Then we ask, is the function or the variable y, whatever it's intended to represent, is its contribution affected in a way that would be beyond a linear form, right? And we define linear as just being, just raised to, a singular power. And, or rather, it's not scaling off of itself or anything, it's scaling based off of other values, right? Because if we had something like, say, I don't know, y times y, right? This is, scaling off of not a, constant, but a changing value as well, which is something that we don't want when we want nonlinearity. And that goes into something called superposition, which again, it starts getting kind of very precise and mathematical, and I want to kind of keep that a little bit light. But essentially all you need to know is that because we have this other variable x being multiplied by y prime prime, then we can say that this is still linear. However, if we had cosine of y times y prime prime plus y prime plus y equals 0, then we would say that this is nonlinear because we have the, again, variable y being used in the cosine function, and then that is now serving as a scaling factor for a derivative of y, and because we have y interacting with itself, even though it's a derivative of itself, then that is no longer good for linear operations, and we have to say that this is now nonlinear. And so it really is kind of boiling down to as simple as that. You just kind of look for if the function y or its derivatives are being interacted with in terms of y. So if we had, say, y prime or y prime prime times y, then that's nonlinear. If we had y prime prime times y prime plus y squared equals 0, well, this is quadratic, so it's instantly nonlinear, right? If we had y prime prime times y equals 0, again, we have y interacting with itself, so it's nonlinear, right? If we had like, I don't know, even if you have some like crazy, thing here like this plus 1 over ln of, or 1 over y prime times ln of secant x tan x, you know, plus y times sine x over cotan x equals e to the negative x squared over 37 x to the 8, right? Even though you see all these other different things for x, right? Even though it's changing in incredible ways in terms of x, because y is still only scaling off of itself, right? It's only contributing in terms of y each time, each individual instance of y, then we would still say that this is, you know, a linear equation in terms of y. If we were asked if it was, you know, linear in terms of x, then obviously that all falls apart, and then yeah, we would say that this is a nonlinear equation in terms of x. And so really that's kind of what you're looking out for. You're really just looking out for it if we ever see, you know, this, or if we ever see, you know, this, or we ever see this, or we ever see, you know, this. These are all no-goes in terms of linearity. That's not what we want to see. We don't want to see y interacting with copies of itself. And then, so if you recall back in Calc 1, you would have learned how to do implicit differentiation. This was actually your first introduction to differential equations. You just might not have realized it at the time, or at least I didn't realize it at the time, what exactly we were learning, because you kind of do it once and then never really do anything with it after that, besides in related rates, which is also more work with differential equations. Of course, it's just not exactly called that at the time, and you're doing kind of very basic ones, where you're kind of given a lot of the equations off, you know, off the rip, and you don't have to do any extra work. But so when we, you know, just doing a quick review, maybe you're given something like x squared plus y squared equals 25, right? And you're asked to find the explicit solution. You know, it's just simple algebra. You know, you would just, you know, if we're solving for in terms of y, of course, we'd move x squared over to the other side, so we get, you know, y squared equals 25 minus x squared, and then of course we would just, you know, square root both sides. So we get y equals 25 minus x squared, and then of course that would be plus or minus, and then we would say that this is the explicit solution in terms of y. But if we're asked, you know, to find the implicit solution of, again, the same expression, right? Then if we differentiate with respect to x, you know, we do d dx x squared plus d dx y squared equals d dx 25, right? And we know this turns into a or since it's constant, turns to 0 for d dx x squared. Of course, that's just 2x. But then because the y squared here, again, this is an implicit solution, so we assume here that since we're differentiating with respect to x, of course, y here actually represents some function, right? So when we differentiate it, we're actually doing y of x squared, right? So then of course we have to use chain rule, right? Because this is, you know, the inner function of that. And so we do the 2x here, but then we just move the 2y. But again, y of x is just represented with y. And then since of course a differentiated function can just be represented in prime notation like this, then we can say that it's just 2y y prime, or, you know, alternatively you could do dy over dx like that, right? But usually a lot more of the time it's more compact to do it in this way. Of course, this is how you would have likely been taught. And then at this point, again, it's just simple algebra. You just move this over here, so it's 2y y prime equals negative 2x, of course, then move that over here, so you get y prime equals negative 2x over 2y, reduce those, so y prime equals negative x over y, and then we would say that this is the implicit solution. And you'll be doing, you know, things sort of like this. Of course, not as simple as that, but just a quick refresher in case you might have forgotten some of that.